So in this class we will take some problems on support reactions. It's an examination problem. July 2016 VTU. So this is the beam. You can see here that the beam is doubly overhanging beam. So it is supported as a hinge supported B and roller supported C. Overhang portions are this AB and CE. It carries a concentrated load at A and another inclined concentrated load at E, 60 kN and 25 kN. The 60 kN is making an angle 30 degrees with the horizontal. And from B to C, we have a trapezoidal load. You can see it has a trapezoidal load varying intensity from 20 kN per meter to 40 kN per meter. And from C to D, it's a triangular load. So we have to find the support reactions. So as you know, there are two supports here. Support B is a hinge support. So normally in case of hinge support, you will be having two reactions, horizontal and vertical, HP and VP, I call them. Then support C is a roller support, wherein you have only one reaction, that is RC, I can say. So totally there are three reactions. After finding HP and VP, you can find out the resultant reaction RB using this formula, root of HA square plus VA square. Now, first thing we have to convert or we have to transform the triangular load, trapezoidal load into concentrated load, and we have to resolve this inclined concentrated load into two components so that we can write the free body diagram of the beam. So let me convert this trapezoidal load into equivalent concentrated load. So you know that trapezoidal load can be split into two, that I have explained. So this is the trapezoidal load from B to C that is given. So the length of the load is 6 meters. This trapezoidal load can be split into two loads. One is UDL, so this is 20 kN per meter, and at this end it is 40 kN per meter. Now you can split this trapezoidal load into two loads. One is this UDL of 20 kN per meter, and another one is this triangle load. So that means this can be written like this: UDL like this from B to C. Intensity is 20 kN per meter, acting over a length of 6 meters. So your total UDL will be, our total load will be 20 into 6, 120, which acts at the midpoint. So equivalent concentrated load is acting at the midpoint, that is midpoint is at a distance of 3 meters from B and 3 meters from C. So let me take this point as F, because last here it is E. I will go for the next letter F. Then you have to convert this triangular load also into equivalent concentrated load. Triangular load varies from 0 to, this will be now 20, because total is 40. 40 minus 20 is 20. So this becomes 20 kN per meter. So this is acting from B to C. Once again it is 6 meters length. You know that the total triangular load can be equated to a concentrated load whose magnitude is equal to the area of the triangle. So area of the triangle is half into 6 into 20, which is 60 kN. So 60 kN is the equivalent concentrated load. You know that 60 kN will act at the center of gravity of the triangle. So G. So this point I will take as G. Now, and you know that the center of gravity or the centroid of the triangle is at a distance of 2/3 from the edge. So 2/3 of 6 meters, which is 4 meters, or it can be 1/3 from the 2/3 from the vertex or 1/3 from the edge. So that means it is 2 meters. So this is how we have to convert the trapezoidal load and trapezoidal load into equivalent concentrated load. On similar lines, this is a triangular load acting from C to D. So that also we have to convert. So here you can see that this triangular load C to D intensity varies from 40 to 0. So this is 40 kilonewton per meter. C to D, the distance is 4 meters. Now we have to convert this triangle load into equivalent concentrated load. Once again, area of the triangle we have to take. So half into 4 into 40, it comes out to be 80 kilonewton. This 80 kilonewton will be acting at the center of gravity of this triangle. I will take this point as H. The equivalent concentrated load is 80 kilonewton acting at the center of gravity or the center of this triangle. Once again, the distance, if you measure, so it will be, this distance to CH will be 1/3 from the end or 2/3 from the vertex. So 1/3 of 4. 1/3 of 4 is 1.33 meters, or it can be 2/3 of 4, which is 2.67 meters. So the HD will be 2.67, CH will be 1.33. So that means I have converted that trapezoidal load and triangular load into equivalent concentrated load, and I have shown where the concentrated load is acting position. Now this 60 kilonewton I have to resolve into horizontal and vertical component. So if you resolve the 60 kilonewton force into horizontal and vertical components, so this angle is 30 degrees. So if you resolve this, horizontal component will be like this, vertical component will be like this. So this is 60 cos 30 because the angle is made with the horizontal. This is 60 sin 30. These two are the components. Now once you get all these things, now you can write the free body diagram of the beam. So this step is very important because conversion of trapezoidal load and triangular load and resolution of this inclined load. Once you do that, now we can draw the free body diagram of the beam now. So A is the beam. So I will mark this is B, this is C, this is D. Now at A you have 25 kilonewton force acting, vertical force, you write as it is. Then from B to C you have trapezoidal load which is converted to two concentrated loads. One concentrated load is acting at F. F is the midpoint here, and the load here is 120 kilonewton. And another concentrated load is acting at G, so which is at a distance of 4 meters. So here it will come. So this value is 60 kilonewton. So let me mark the distances. Distances are very, very important because we are taking the moment. So distances upon this point is D. Yes. Now from A to B you have 3 meters. B to F also 3 meters. F to G. So F to G it is 4 minus 3, 1 meter. Then G to C is 2 meters. Yes. Now coming to this triangular load from C to D, you have the triangular load is equivalent constant load is 80 kilonewton, which acts at the CG. So that H point H. So this is H. So distance from C to H is 1.33 meters, and from H to E is 2.67 meters. So that force is acting here, which is equal to 80 kilonewton. 80 kilonewton. Now at the last you have that at point E you have inclined load. So that inclined load we have resolved into horizontal and vertical component like this. So this is 60 cos 30, this is 60 sin 30, and the distance from D to E is 2 meters. So this is how we have to write the free body diagram. So in the free body diagram, all the other loads are converted to equivalent concentrated loads, and the inclined loads are resolved, and we have to write the reactions also. Here, as I told that HP and VB are the horizontal reactions here. So what I can do here is the only the 60 cos 30 is acting like this in this direction. I can take the reaction acting in the opposite direction, I can assume. Or even if you assume in the same direction, you get the value negative. So what I do here is HB, I will take like this. This is HB, which is one of the unknowns. Then I will take VB like this. So HB and VB are the reactions at B, and at C you have molar support, you have vertical reaction RC here. So this is RC, only one reaction is there. So these three reactions we have to find out now by using the three equilibrium equations. So let us write one by one. The first equilibrium equation. So three equilibrium equations we have to use. The first equation is sigma Fx is equal to 0, forces acting towards right positive, left negative. So you have only two forces. One is Hp, that is the reaction, which is acting towards right. Therefore Hp I will take positive. This is acting towards left. Minus 60 cos 30 is equal to 0. Therefore directly you can get the value of Hb. 60 cos 30. So 60 into cos 30 is 51.96. 51.96 kilonewton. That is the reaction. Since you have got positive value, your assumed direction of Hb is correct. So Hb is acting like this. So 51.96 is the value of Hb, which is acting towards right. Now second equilibrium equation I will be using. The second equilibrium equation is sigma Fy is equal to 0. That is the algebraic sum of all the forces in the y direction, vertical direction. I am going to take it as 0 for the equilibrium. You have three equilibrium equations for non-concurrent force system, as you know. So second equation I will write sigma Fy is equal to 0. Sign convention is upward forces positive, downward forces negative. So here you can see these two reactions, VB and RC, they are upwards, so they become positive, VB plus RC. All the other forces are negative because downwards. Minus 25, minus 120, minus 60, minus 80, minus 60 sin 30 is equal to 0. Now if you simplify this, you get VB plus RC is equal to, all these become plus, it is written to the RHS, 25 plus 120, 145, 145 plus 60, 205, 205 plus 80, 285, 285 minus plus 60 sin 30 is 30. So 285 plus 30, I think it is 315. Please check your value. 315 is the, you cannot solve this because there are two unknowns. All this has equation 1. Now the third equation is the moment equation. So moment equation, you can take the algebraic sum of the moments of all the forces and reactions about one of the supports and you can equate it to 0. What I do is I will take sigma mb is equal to 0. So clockwise moment positive, anti-clockwise negative. So now I am here. Be careful here. Now moment is nothing but the magnitude of the force multiplied by the lever arm or the moment arm or the perpendicular distance to the layer of action of the force from the point. So now 25 kilo, one by one I will take. This 25 kN is giving an anti-clockwise moment, so it is negative. So minus 25 into distance is 3 meters. I am taking about the point B. This 120 kN is giving clockwise moment, distance is 3 meters, so plus 120 into 3. Please note that this HB and VB, they are not giving any moment about the point B because the lines of action are passing through that B. Now coming to 60 kN, it is giving a clockwise moment and the distance from B to the 60 kN is 4 meters. Therefore plus 60 into 4. Then coming to this 80 kN, this RC. So don't forget this. RC is giving an anti-clockwise moment about B. So RC into distance is 3 plus 1 plus 2, that is 6. So minus RC into 6. Then coming to this 80 kN, it is giving a clockwise moment. So plus 80 into distance from B to this 80 kN is 6 plus 1.3, 7.33. So plus 80 into 7.33. Then you have to take this 60 sin 30. So that is also giving a clockwise moment, 60 sin 30 multiplied by distance from A, that B to E is 6 plus 4 10 plus 2, 12 meters. And the 60 cos 30, if you extend this line of action, it passes to the point B, therefore moment due to this will be 0. So therefore all the forces and reactions we have considered, RHS becomes 0. So 25 into 3, once again you can check, it is negative anti-clockwise, plus 120 into 3 clockwise, plus 60 into 4 clockwise, minus RC into 6 anti-clockwise, plus 80 into 7.33 clockwise, plus 60 sin 30 into 12 clockwise. So is equal to 0. Now if you simplify this, let us check what is the value you are going to get. So you are going to get, if you want this 6 times RC, you can bring to RHS, it becomes positive. All the other terms you can keep it in LHS. So minus 25 into 3 is minus 75. Do it carefully. Plus 120 into 3 is 360. Plus 16 into 4 is 240. Then plus 80 into 7.33. Then plus 60 sin 30 is 30. 30 into 12 is 360. So plus 360. So this value becomes 1471.4. 1471.4. Therefore RC is 1471.4 divided by 6. So it becomes 245.23. 245.23 kilonewton. Since the value of RC is positive, our assumed direction of RC upwards is correct. So the value of RC, we got it as 245.23. Now, once you get the value of this RC, we can find out the other vertical reaction, that is VB, by substituting for RC in this equation 1. So substituting for RC in equation 1, you can get the value of VB. So now I will write here, substituting for RC in equation 1. RC in equation 1. So you will get VB is equal to 315 minus RC, which is 315 minus 245.23. So if you simplify this, you will be getting 315 minus 245.23, which is comes out to be 69.77. 69.77 kilonewton. So the value is positive, that means assumed direction is correct. So 69.77 is the value of VB. Now, once you get these two, now we got the value of RC, we got the value of HB and VB. Since this hinge and you have two reactions, that can be replaced by a single resultant reaction. So resultant reaction I can replace RB. So RB is equal to square root of HB square plus VB square, and also you can find out the angle with which the resultant reaction makes with the horizontal. So I will write resultant reaction RB will be square root of HB square plus VB square. So which is nothing but 51.96 square plus 69.77 square. So if you do the simplification, so you will get the value of RB as 51.96 square plus 69.77 square under root. So you will be getting 86.99 or 87. So 87 kilonewton is the magnitude of the resultant reaction at B. Now I have to show the direction. Since HB is like this, it is acting towards right, and VB is like this. So definitely RB will be like this. So arrow should meet, that is the meaning. And if you take this angle as alpha, alpha is the angle made by RB with the x-axis or horizontal. So I can take alpha as tan inverse of modulus VB by HB. which comes out to be tan inverse of 69.77 divided by 51.96 modules. So that means you will be getting 69.77 divided by 51.96. So tan inverse of that, so you will be getting 53.32 degrees. 53.32 degrees. So this is the angle with which that reaction at the resultant reaction at B makes with the horizontal. Now after getting all this, now you can show the reactions plotted in the diagram, something like this. So just I will show the beam like this. E is there here, A is there, A is there here, B is here, C is here, D is here. Just only I will show the reactions. So RB is actually in the first quadrant, you can see. So RB reaction will be like this. The value of this RB is 87 kilonewton, and the angle made by this RB with the horizontal is alpha, which is 53.32 degrees, and the reaction at C is vertical, that is RC, which you have got it as 245.23 kilonewton. So this is how the reactions we can show in the diagram. Please note that RC is very much higher than RB. You can see RC is very much higher than RB. That is because near C, support C, more load is active. You can see the concentration of the load near the support C is more. You have C, you can see here to the left of C you have got trapezoidal load, to the right of C you have got triangular load. So that will have more effect at the support C. So that whereas at B, 25 kilonewton is acting at some distance 3 meters. It's at far away distance. That means what you can say, what you can conclude is reactions at the supports which are nearer to the higher load intensity will be higher. So if the support is subjected to more load near that support, then the naturally reactions values will be very high. So this is an important problem. So why I took this problem is, here there are so many things. We have to convert this trapezoidal load into two concentrated loads, triangular load into concentrated load, and inclined load we have to resolve. Then at hinge support we have two reactions, horizontal and vertical. Roller support we have only one reaction, vertical. Then since there are three unknown reactions, we have to use three equilibrium equations, one by the other. Then at the hinge support, after finding the two reactions, we have to find the resultant reaction along with its direction.